So next up, we have Sabyasachi. He is a PhD, or he's a postdoc here at the observatory at the moment. He got his PhD at the University of Wisconsin-Madison, and he's working in the optics lab setting up the new IFU for the STOBIE spectrograph on SALT.
Can you hear me? Okay. So slight correction, I did my PhD in India. I did my first postdoc in US, in Wisconsin. Anyway, myself, Sabyasachi, and thanks for having me here. I'm going to talk about my ongoing work at SAO, the SLIT mask IFU for the STOBIE spectrograph. My main collaborators are Professor Matt Bersetti, who is actually time sharing between UW-Madison and in SIO, as well as Marsha Wolf, Mike Smith, and Joshua Hopper, who are all from UW-Madison. Okay, I would start with the SALT prime focus assembly, which you are seeing here in this slide. As you may know, the SALT is a fixed elevation telescope at 53-degree angle. So the tracker at the prime focus has to move around, actually track the object during the exposure. The primary mirror sitting somewhere below on the left corner on the image, and then that sends the light and it goes through the spherical aberration corrector. And then which actually feeds the light to the suite of instruments, which is sitting on the top. I marked it with the instrument assembly. And then you see this hexapod, which is giant size. It actually helps in active positioning. So that's with the telescope. Coming on to the RSS spectrograph itself. So this is the model of the spectrograph. The light actually comes from the bottom, and I marked the SLIT mask, which actually gives the light in a one-dimensional array of photons. So it's basically a one-dimensional slit. And then it fits the collimator via the fold mirror. Then the collimated light is then diffracted by the grating, and finally that deflected within the top plane before getting focused on the detector by the collimator. Sorry, by the camera optics. In terms of specification, the RSS covers from 390 to 900 nanometer in wavelength at a spectral resolution of maximum 6,000. The slit length is 8 arc minute, which is basically 106 mm in linear dimension. And also there are several slit masks varying width, and these are typically kept on the rack, which is actually it's showing on this side. And these are actually drawn from this cartridge, the slit mask, and then fed to the position with the elevator. Okay, going on to the slit mask itself, this is the mechanical model of it. And you see the central aperture, which is kind of open right now, but it's actually it's narrowed down by two knife edge glass plates with precision separation. As you may see that the 130 mm length and similar width, along with the 8 mm thickness, it's basically a DVD size cassette. And there is a notch on the bottom left. You can see in the front. That's for just a towing from the elevator and placing it in the elevator. There's a cutout for linear holding, and on the other side there is a T slot which I have marked. That's for just loading it up and down within the SALT elevator. The focal plane actually sits right into the middle of the slit mask, which is like 4 mm from the top or the bottom surface. Here is an image of the slit mask on the elevator floor. Moving on to it, I just wanted to give you a brief discussion what is the instrument looks like. So we are just basically planning to replace the slit mask with an integral field unit. I'm going to talk about what integral field unit is a little later. But before that, let me just describe the most stringent mechanical constraints we have from the slit mask itself. So firstly, the entire IFU has to fit inside the mechanical envelope, the DVD cassette size envelope of the slit mask. And the most constraining requirement is the 8 mm thickness. On top of that, the unit has to have the strong walls so that Any kind of movement within the elevator or from the cartridge doesn't hamper the internal parts. And finally, we want to use the entire slit length of the 106 millimeter or the 8 arc minute, and we don't want to lose on the sky coverage. Before going into the details of this issue, let me just describe what IFUS spectroscopy is. It's basically in long slit spectroscopy, the light is fed through a narrow slit, which I described as a slit mask. This is usually the slit is as wide as the sky seeing, and then the optics is aligned in such a manner that the light gets dispersed perpendicular to the length of the slit. Now, if I talk about the IFUS spectroscopy, it's generally what happens is that a two-dimensional area on sky is reformatted into one-dimensional slit via, it can be a reflective element or it can be a transmissive element. And there are multiple ways to do that. So for example, on the top one, the top option, which is just the lenslet. So a 2D array of very small lenses, it can be 50 micron, it could be 1 millimeter, but these lenses are very small. And we use a 2D array of these field lists at the input plane. And what happened is that the spectra is then recorded with careful alignment of the optics. And obviously, if you see the spectrograph output, that's the third column here, that the spectral resolution as well as the wavelength coverage are seriously restricted. Somewhere it is cut off, somewhere it's too small, and somewhere it's overlapping, in fact. The second option which we are using is just fibers. So basically, instead of lenslet, we put a 2D bundle of fibers. The 2D array of fibers collect light, and since they're flexible, we can just move in them to form a single one-dimensional slit. And the fibers IFUS are generally very helpful for optical wavelengths. I would come to the reasons later. Basically, the point is that the third option, sorry, before letting in that, let me talk about the third option, which is the image slicer, which is I'm showing in the third, the bottom row here, is the image slicer. So you just divide the field with a set of mini reflective mirrors, and then you set your reflective path in such a way they form a 1D slit. And this option yields very high throughput compared to fibers, high in the sense at least 10 to 15% itself easily. And then the problem with these is that in optical wavelengths, we can't just use this. They are very good for near IR because you have to polish the optical surface to very high accuracy, something like λ/8. And that high accuracy, given your wavelength is decreasing from ever decreasing, if you go into bluer and bluer wavelengths, is very high. I mean, it actually drives the cost very high. So I would just say that if you just look at the final product is from an IFUS spectroscopy, is that the spectrograph records all this light, and then there's a backend software. That backend software just reformats and just keeps the data in a 3D cube so that you have both the spatial and spectral information intact. Now let me just talk about why do we need IFUS spectroscopy for SALT. So IFUS spectroscopy has these inherent positives. You do not have to scan through an extended object with long slit, with multiple exposures. In those multiple exposures, the seeing or the sky condition may change, but rather in one coherent shot, you would capture the entire 2D spatial information as well as the wavelength information. The important aspect of using a fiber IFU is to use the scrambling property. So this is very important. The scrambling property is basically, it's a property by which the fiber scrambles the input spatial information while transmitting the light from its input to the output. You could think it as the loss of information because basically all the information within the fiber input is lost. But we are not bothered about that detailed information, and especially because it is our fiber sizes are close to the seeing, we are not basically losing much. But in terms of the difference in fiber, I mean, fiber to fiber information, which is the spectra to spectra information, that information we are gaining. So we are basically digitizing or the spatially resolving an extended object. I would just describe it a little bit given this slide. So for example, you have a very diffuse gas emission, which is substantially fainter than the night sky. For such observation, we obviously need the photon-limited sky subtraction. The spectrograph requires an exquisitely homogenized pupil invariant of the field position, which means that even if it moves on the focal plane, it has to be a homogenized, which is that there should not be any variation in the pupil light distribution. The SALT pupil, on the other hand, is time varying, as I am showing on the top panel. And then what happens is that the SALT pupil time varying thing happens, and it happens over the track, which means within an exposure. And then this thing does not help. I just wanted to show you how that affects. So basically, if you see that the bottom line, there is a direct beam which has been vigneted. And we are vigneting the direct beam on its pupil so that, the direct beam is three type of different beam. So the three converging light beams are fed through optical fibers. One is right at the center of the fiber, one is at the edge, and one is somewhere between the edge and the center. And you see there's a near field pattern and there's a far field pattern. And the patterns are actually changing because of basically the near field pattern is basically changing depending on the input spot if you use the direct beam kind of vigneted. However, what we basically require is the far field for the spectrograph. So we won't care about the near field. But the problem is there that if you don't use any kind of fiber scrambling, you would find such situation, which is the near field would get projected in the detector. And which actually Smith et al. Actually tried this using different fibers, which fiber is the best. So they have used octagonal fibers, which is the right side triangle, tridentate, and the left side trident, which is like the circular fiber. And they found that the circular fibers are much better in scrambling the far field, which is important to us. The octagonal fibers are good in near field, but not so good in the far field. So we just went ahead with the circular beam, which is most common. I'm just going to give you another example of the same effect. So there's a Hadron galaxy on the very left, which has been observed with this SALT long slit. And the top panel is the objects plus sky, while the bottom is the sky only. As you can see, the sky subtraction is not optimal, and the red arrows point to sky lines in the subtracted frame, which is in the middle. Since SALT is at a fixed elevation, the payload has to track the object, resulting in a variable pupil. Over the track or exposure, the strength of the skyline would change, obviously. Ideally, one would have to get the sky flats in a baffle system that would generate the exact shape of the pupil, which is basically practical because you have to do it for each object separately. Which you have a flat for each object mimicking its exposure in its vigneting of the pupil over the track. So that's basically it's inefficient, as I must say. So, however, if you use the fiber, that information is, that part is redundant. We don't need to do any of this. So with the fiber just scrambles the input, leaving out no trace of the variation of the input at the output spectra. And this in turn proves the uniformity of the spectrograph response. So yeah, that's really, really good for an instrument like, telescope like SALT. Okay, let's move on to the instrument description. So here is the slit mask IFU. I just exploded the top and just lifted the top plate, and you would see the central structure. So if you just look at the inside, so you'd see that there's a place where the long slit prisms are mounted, and the prisms are I just mentioned at slit prisms, but there are also IFU prism, which is sitting below the slit prisms. On the other side of the prism, there is on one side there is a gray bar, which is the integral field unit. It's basically a bunch of 2D fibers. On the other end, there is a red and blue colored fibers are arranged in a one-dimensional slit. Okay, so let me just clear it up. So I removed some of the components and just showing you it from a different angle. So there are two slits for the two prisms for the IFU, and there's one prism for the two prism for the slit and one prism for the IFU. All the prisms have the same dimension, have the hypotenuse coated with reflective coating with 95% or higher reflectivity over the wavelength range. The cross-section is shown on the right panel of the prisms. And you could see that the prisms together the height of these prisms together is right under 8 mm, which is like 7.612 mm here. This eliminates any chance of scratching the surface, which is, it's barely, but it's not going to scratch any of the optical surface. And the light comes from the telescope below the bottom window shown in the top left mask button, and then enters the prism via one of the legs. The IFU prism is represented by the red triangle at the bottom of the right panel. The track of the light in air is marked by the blue rays. The prism acts as a fold mirror and reflects a focal plane onto the other leg shown by the green rays here on the right. And then basically, in the absence of the fold prism, the light would just pass through, goes through as shown by the blue ray, forming the telescope focal plane. Okay, so here are the IFU and SLIT prisms. Okay, the fiber bundle, the 2D object fiber bundle, the light comes, gets passed into those fibers. The fibers comes out of the back plane, and then they get routed to the slit on the opposite side of the prisms by 2 channels, left and right, while maximizing the bending radius. So we have to think about the non-telecentricity issue as well. So there are 2 sky fiber bundles as well, and they are separated by more than 100 arcseconds from the center of the object fiber. So fiber comes out of these bundles and get routed in the similar manner, just like the object fibers. Although the sky bundle offers synchronous aperture, the sky subtraction is not optimal using the sky bundles, as solid focal planes suffer from high non-telecentricity. And finally, the fibers fed the light into the slit prism via the air-coated leg. You can see it here. The slit prism folds the light back into the spectrograph. However, the spectrograph would continue to be focused on the telescope focal plane. So basically, we are not changing the position of the focal plane, which means that the spectrograph and the telescope does not have to be changed, which means that the IFU, or the slit mask IFU, in fact, is basically become a modular, interchangeable, and kind of a plug-and-play device. Coming on to how the instrument would look like on the slit side. So there is a 0.9 arcsecond fibers, which would sit on these V-groove, which is prototyped by the SAO machine shop. There are various options. We actually plan to have 5 variants of the IFU, ranging from 0.9 arcsecond spatial sampling to 2.7 arcsecond spatial sampling. And you may notice that with bigger fiber size, the total area on the sky is actually increasing. Well, that is one of the positives to cover a bigger object in a single exposure. The other thing you must note that the gap between the spaxels are increasing, which means that the sampling is getting sparser. On one extreme, the other extreme is that if you use the smaller fiber, 0.9 arcsecond, the spatial resolution actually increases quite a. The spectral resolution increases quite a lot. And finally, I want to point out that there's a near IFU which is being developed at the University of Wisconsin, which is actually mimicking the 300 micron 1.4 arcsecond fiber IFU. And so that would give a panoramic coverage from very blue to the middle of the J or K band. In fact, J or K band. That's a panoramic view you can have with near IR IFU and the slit mask IFU together. So, sorry. Let me just talk about what all science you can do with it. So basically, the IFU is edge-on, so it is well optimized for extended hexagonal shape. So well optimized for edge-on galaxies. So one could spatially map the stellar or gas dynamics, chemical composition, star formation from, for example, thick or thin disk halo interface, all those stuff. You can do it easily for the edge-on galaxies. But you can also do face-on galaxies or slightly less inclined galaxies as well. You can just look at the very central part of the nearby galaxies, or If it is far away galaxies, you can actually cover the entire galaxy with the bigger or the medium size IFUs. But if you're in the intermediate redshift, you can actually look at the cluster, multiple galaxies you can look at, and it's a single exposure. Also, you might want to look at specific galaxies in detail, or you can look at peculiar objects like giant arcs, which are quite lensed objects. So yeah, that's all we can do. There's more things you can do. You can just have to think about what all you can do with it. Just comparing with the other instruments, I think.
Sorry, Sabyasachi, we've
yes.
I think we've run out of time.
Yeah, just gives 30 seconds to wrap this up.
Okay.
So I just wanted to compare that the SLIT mask is quite comparable to the other 10-meter class telescope with MUSE and Keck cosmic imager in terms of wavelength range and the field of view, spectral resolution as well. So that way it's quite comparable. And finally, just this update on that, we are almost ready with all the mechanical designing as well as polishing, optical design. Some of the parts are being manufactured here at SAO, and we all think that we could finish it by the end of December 2021. Yeah, that's all. Thank you.
Okay, so I just have one quick question. I know space is really packed up at the top of the Robert STOBIE spectrograph. Is this a problem for you, routing all those fibers, getting all those bundles together and putting them in such a small space?
Yes. So ideally, the fibers are very fragile if you bend them. So for example, with this RSS, so the SLIT mask has very small coverage. I think we have to do very well to route it through those small spaces.
All right. Thank you very much.